the universe stretches outward without end. We exist within an eternal ocean of celestial bodies, planets circling distant suns, stars burning through their nuclear fuel, entire galaxies spinning through the cosmic dark, all extending in every conceivable direction for distances that exceed our capacity to truly comprehend. This is the narrative we've constructed, the story we tell ourselves about our place in existence. Yet when we turn our gaze upward on a clear night, when we look past the familiar constellations and peer into the depths beyond, we don't witness an infinite luminous glow filling every corner of our vision. What confronts us instead is absence, darkness, an impenetrable black that seems to mark a boundary of some kind. But this darkness doesn't represent the terminus of the universe itself. Rather, it signifies the limit of what we can observe, the horizon beyond which our instruments and our understanding begin to fail us. The span between our present location and the furthest reaches of what we can detect stretches approximately 46.5 billion light-years in any direction you choose to measure. This creates a vast spherical domain of observable space, a bubble of knowable reality that measures roughly 93 billion light-years from one side to the other. To understand this distance, we first need to grasp what a light-year actually represents. It's not a measure of time, despite the name. A light-year quantifies the distance that electromagnetic radiation light can traverse during the period it takes our planet to complete one full orbit around its parent star. Light propagates through the vacuum of space at an unchanging velocity, and according to everything we understand about physics, nothing with mass can exceed this speed. This fundamental constraint serves as one of the bedrock principles governing cosmic behavior. We therefore measure astronomical distances by calculating how long light would take to cross them, moving at its constant maximum velocity. For our observable sphere, that journey would require 93 billion years if you could somehow travel from one edge to the other at light speed. Within this enormous bubble exists everything humanity has ever perceived. Every observation we've recorded, every piece of data we've collected about reality. Somewhere near the precise geometric center of this sphere, you'll find our solar system, our world, and every human being who has ever lived. We occupy the position of observer, and this role places us at what we might call the center of our own perceivable cosmos. The universe doesn't actually have a center, not in any meaningful sense. But from our perspective, we unavoidably occupy that central vantage point within the sphere of what we can detect. Now we arrive at something genuinely strange, something that challenges our intuitive understanding of how light and space behave. The boundary that separates our cosmic bubble from whatever lies beyond isn't actually dark at all. In fact, it's quite the opposite. The edge of our observable universe is composed of light, though not the kind of light we're accustomed to experiencing in our daily lives. This is ancient light, primordial radiation. The first electromagnetic waves that emerged from an era when the universe existed in a state of extreme density and temperature. The entire cosmos was once compressed into a condition of such intensity that matter as we know it couldn't yet exist. This moment of transition, this emergence of the early universe, has come to be known as the Big Bang, though that term is profoundly misleading. The phrase suggests an explosion, a detonation that sent matter flying outward from a central point. This isn't what happened at all, but we'll examine the actual nature of cosmic expansion shortly. For now, what matters is understanding that this first light exists out there at the very limits of our detection capabilities, marking the boundary between what we can observe and what remains forever beyond our reach. The reason we perceive blackness when looking into space, rather than being overwhelmed by this ancient light, has to do with the limitations of human vision. Our eyes evolved to detect electromagnetic radiation within a specific range of wavelengths, what we call the visible spectrum. Light can be understood as a wave phenomenon, similar to ripples spreading across the surface of a still pond after you've tossed a stone into the water. At the point of impact, you see tight, well-defined waves with distinct peaks and troughs. As these waves propagate outward from where the stone entered the water, they spread into increasingly wider circles. The distance between successive peaks grows larger, and the height of each peak diminishes. Eventually, at sufficient distance from the impact point, the waves become so spread out that they're essentially invisible to an observer watching the pond's surface. But the disappearance of these waves from visibility doesn't mean their influence has truly ended. The energy from that stone's impact continues traveling through the water, And with sufficiently sensitive equipment, you could detect its effects even at the pond's farthest edges. You simply need an instrument capable of measuring those subtle, lingering vibrations. This is precisely why we construct sophisticated observational tools like the James Webb Space Telescope. This remarkable instrument possesses the ability to detect light in ways that biological eyes cannot. When light waves stretch beyond a certain point, when the distance between successive peaks becomes too great, that light shifts out of the visible spectrum and enters a range we call infrared. You've likely encountered this term before. Devices like night vision goggles can detect infrared radiation, which allows them to form images in conditions that would appear completely dark to unaided human vision. However, even night vision technology only captures relatively nearby infrared sources. You can't point night vision goggles at the sky and suddenly see the light from the universe's beginning. The James Webb Space Telescope operates at a completely different level of sensitivity. It can detect light that has shifted far deeper into the infrared range than any night vision device could hope to capture. Through its instruments, the apparent blackness of space reveals itself to be filled with light that simply exists outside our natural perceptual range. James Webb can observe deeply into our cosmic bubble, capturing images of galaxies and stellar formations that existed billions of years ago. Their light only now reaching our corner of space. Yet even this extraordinary instrument has its limits. Beyond the most distant galaxies it has photographed, beyond the faintest smudges of light it can detect, the void remains. So if even our most advanced telescope cannot see the edge of observable space, how can we claim that light exists there? The answer requires us to dive even deeper into the electromagnetic spectrum, to venture so far beyond visible light and even infrared that we enter territory most people would never associate with illumination at all. We're surrounded by microwave radiation. It reaches us from every direction, a faint background signal that pervades all of space. Not the microwaves that heat your food, that's just a convenient name for that kitchen appliance. What we're discussing is electromagnetic radiation with wavelengths longer than infrared, radiation that has traveled across such vast distances that it has been stretched into this extremely low-energy form. We cannot see it with any optical instrument, but we can measure its presence with specialized detectors. Hidden within these measurements, encoded in the subtle variations of this microwave signal, we find evidence of the universe's first light. Scientists call this the cosmic microwave background, abbreviated as CMB. This is what exists at the edge of our observable sphere. We visualize the CMB by creating what's called a heat map, a color-coded representation of the tiny fluctuations in microwave intensity across the sky. The images you may have seen, typically showing swirling patterns of blue and yellow, don't represent actual colors. These are false color representations designed to highlight small differences in the microwave frequency from one region of sky to another. What these maps reveal is profound. The universe has never been uniform. Even at its earliest observable moment, slight variations in density existed. This makes intuitive sense when you consider how matter is distributed in the present universe. Galaxies aren't scattered evenly through space like points on a perfect grid. Instead, they cluster together in higher density regions, forming vast cosmic structures, walls and filaments of galaxies, separated by enormous voids containing relatively little matter. The pattern we see in the CMB mirrors this clumpy distribution, showing us that these density variations existed from the very beginning. But the most fundamental insight we gain from measuring the CMB comes from analyzing its wavelength. The degree to which this light has been stretched tells us how long it has been traveling, and therefore how old it is. Through careful measurement and analysis, scientists have determined that the light forming the CMB is approximately 13.8 billion years old. This number represents the age of the observable universe itself, or at least the age of the earliest light we can detect. Now we encounter a serious problem. A mathematical contradiction that seems to violate the rules of physics. We've established that the CMB is 13.8 billion years old, meaning this light has been traveling toward us for that entire duration. We've also established that the edge of our observable universe lies 46.5 billion light-years away. If light travels at a constant speed, and if nothing can move through space faster than light, then how can 13.8 billion-year-old light be 46.5 billion light-years distant? The numbers simply don't work unless we're missing something fundamental about how the universe operates. To resolve this paradox, we need to revisit the early 20th century and the revolutionary work of Albert Einstein. Einstein developed his theory of general relativity, a mathematical framework that describes the fundamental relationships between space, time, gravity, and light. His equations explained how massive objects curve the fabric of space-time, how this curvature produces what we experience as gravitational attraction, and how light follows the straightest possible path through this curved geometry. But Einstein, despite his genius, made a significant error in his initial understanding of cosmic structure. He believed the universe must be static and unchanging, an eternal arrangement of stars maintaining fixed positions relative to one another. This wasn't a unique misconception. Most physicists of his era shared this assumption about the cosmos. The problem Einstein encountered was that his own equations predicted such a static universe should be impossible. Gravity, as described by general relativity, acts as an attractive force between all masses. If the universe were static, this mutual attraction should cause everything to gradually pull together, eventually collapsing the entire cosmos into an increasingly dense state. Einstein found this conclusion unacceptable. To preserve the static universe he believed must exist, he introduced an additional term into his field equations, which he called the cosmological constant. This constant functioned as a repulsive force, a kind of anti-gravity inherent in empty space itself. Its purpose was to perfectly counterbalance gravitational attraction, maintaining the universe in a stable, unchanging configuration. The fascinating aspect of the story is that Einstein was wrong about the static universe, but his cosmological constant turned out to be correct. He simply didn't realize it at the time. Advancing to the middle of the 1920s, we encounter Edwin Hubble, an astronomer whose observations would transform our understanding of cosmic structure. Hubble made the first definitive proof that galaxies exist as distinct entities separate from our own. Before his work, the prevailing assumption held that every point of light visible in the night sky was simply a star within our own stellar system. Astronomers had noticed numerous large, bright, diffuse objects that appeared somewhat cloud-like through their telescopes. The assumption was that these fuzzy patches called nebulae were clouds of dust and gas located between stars within our own system. The largest and brightest of these nebulae was Andromeda, a smudge visible even to the naked eye under dark skies. Hubble set out to determine the actual distance to this nebula. His method relied on identifying a special type of star called a Cepheid variable. These stars are remarkable because they pulsate, alternating between bright and dim states in a regular, predictable pattern. Astronomers had discovered a relationship between the period of a Cepheid's pulsation, how long it takes to complete one cycle from bright to dim and back to bright, and the star's intrinsic luminosity. Slower pulsing Cepheids are intrinsically brighter than faster pulsing ones. By measuring the pulsation rate, you can determine the star's actual brightness, how much light it's genuinely emitting. Hubble managed to identify Cepheid variables within the Andromeda Nebula. By measuring their pulsation periods, he determined they must be extraordinarily luminous objects. Yet, through even the best telescopes, they appeared remarkably dim. This could only mean they were incredibly distant. Hubble's conclusion was inescapable. Andromeda couldn't possibly be a simple cloud of dust within our local stellar neighborhood. It had to be an enormous collection of stars, so remote that all its individual stars merged into a hazy glow. This was humanity's first solid evidence for the existence of galaxies, island universes scattered throughout space, each containing billions of stars. Hubble's next major discovery was even more revolutionary. Not only do these galaxies exist, but they're in motion. Specifically, they're moving away from us. Hubble collaborated with Vesto Slipher, who had been studying the light from nebulae for years. Slipher noticed something peculiar. The light from nearly every galaxy showed a shift toward the infrared end of the spectrum. We've discussed how light behaves as a wave, and how stretching these waves makes them shift toward longer wavelengths, moving from visible light into the infrared range. But what causes this stretching? The answer lies in a phenomenon called the Doppler effect. You've almost certainly experienced the Doppler effect with sound waves. When an emergency vehicle approaches you with its siren blaring, the pitch of that siren sounds higher than it actually is. As the vehicle passes and moves away, the pitch drops, becoming lower than the siren's true frequency. This happens because sound consists of pressure waves traveling through air. When the source of sound is moving toward you, each successive wave pulse is emitted from a position slightly closer to your location. This compresses the waves together, reducing the wavelength and increasing the frequency, which we perceive as a higher pitch. Conversely, when the source moves away, each wave is emitted from a position slightly farther from you, stretching the waves out and lowering the frequency, which sounds like a lower pitch. Light obeys the same principle. When a light source moves toward an observer, its wavelengths compress slightly. Shifting toward the blue end of the spectrum, this is called blue shift. When the source moves away, the wavelengths stretch, shifting toward the red and infrared end redshift. The degree of shift directly correlates with the velocity of the source. Hubble and Slipher's observations revealed that nearly every galaxy shows redshift, meaning nearly every galaxy is moving away from us. Even more remarkably, Hubble discovered a pattern. The farther away a galaxy is, the greater its redshift, and therefore, the faster it's receding. This discovery fundamentally altered our understanding of cosmic structure. It revealed two critical facts. Space itself is expanding, and the rate of this expansion is accelerating over time. Einstein's vision of a static universe was definitively wrong. The cosmos is dynamic, constantly growing larger. But we still needed to explain what drives this expansion. Here, Einstein's cosmological constant finally found its proper role. The force of cosmic expansion isn't balanced against gravity, it's stronger. The cosmological constant, or what we now call dark energy, represents the energy inherent in empty space itself. This energy produces a repulsive effect, pushing regions of space away from each other. Here's where it gets genuinely bizarre. Dark energy's influence increases with distance. The more empty space exists between two objects, the more dark energy there is pushing them apart. As they separate, even more space opens between them, which contains even more dark energy, which pushes them apart faster. This creates a runaway acceleration effect. The expansion of space can and does exceed the speed of light. Einstein's rule that nothing can move through space faster than light remains valid. Matter cannot exceed light speed relative to the space it occupies. But space itself isn't bound by this limit. Space can expand at any rate, carrying distant galaxies away from us faster than light could ever travel the distance between us. This resolves our earlier paradox. The CMB is indeed 13.8 billion years old. That light has been traveling toward us for that entire span. But during those 13.8 billion years, space itself has been expanding. The point in space where that light originated has been carried away from us by cosmic expansion and is now 46.5 billion light-years distant. Light travels at a fixed speed limit, while space itself can accelerate indefinitely. To fully grasp what cosmic expansion means for our understanding of the universe's origin, we need to fundamentally reconsider the Big Bang itself. We need to discard the simplified, misleading explanation that most of us absorbed during our education. You were likely taught that the universe began as an infinitely dense point, sometimes called a singularity or cosmic egg. Then this point exploded, violently releasing all the matter and energy that would eventually form stars, galaxies, and everything else we observe. This narrative is appealingly simple. It creates a clear mental image, an explosion from a central location, matter flying outward in all directions, gradually cooling and organizing itself into the structures we see today. If everything is currently moving apart, the logic goes, then running time backward should show everything converging back to a single point of origin. But this mental model is fundamentally incorrect. The universe didn't expand outward from a single location like fragments from a detonating bomb. Consider our cosmic bubble again. That sphere of observable space bounded by the cosmic microwave background. That ancient light surrounds us completely, forming a perfect spherical shell in every direction we look. The Big Bang didn't occur at some distant point in space from which light and matter have been traveling toward us. Instead, the Big Bang happened everywhere simultaneously. Every point in space experienced this event at the same moment. The entire universe, not just our observable portion, but the entire cosmos, which may well be infinite in extent, underwent a nearly instantaneous expansion from whatever size it was before to something vastly larger. We don't know the actual size of the pre-expansion universe. We may never know. But we're reasonably confident that this expansion occurred in an almost incomprehensibly brief instant, a fraction of a second so small it challenges our ability to conceptualize time. During this period, known as cosmic inflation, A region of space the size of a single grain of sand might have expanded to the size of an entire galaxy. Now attempt to imagine a sandbox filled with countless grains of sand. Picture every single grain simultaneously expanding to galactic proportions, all at once, everywhere. And understand that even this comparison doesn't begin to capture the true scale of what occurred, because the universe is vastly larger than any sandbox analogy can represent. This inflationary period solves several puzzles that had troubled cosmologists. One question that had long perplexed scientists was why the universe appears so uniform on large scales. When we look at the CMB, when we examine the distribution of galaxies across enormous distances, we find that conditions are remarkably similar in regions of space that are so far apart they couldn't possibly have influenced each other through any known physical process. If the universe had expanded at a constant rate from the beginning, regions on opposite sides of the observable universe would never have been in contact. They would have been too far apart for light or any other signal to travel between them. So why do they have nearly identical properties? Why is the temperature of the CMB almost exactly the same in every direction we look? Cosmic inflation answers this question. Before the inflationary expansion, the entire region that would become our observable universe was incredibly tiny, small enough that all parts of it were in thermal contact. Physical processes could even out any initial irregularities, creating a uniform state. Then inflation occurred, explosively stretching this tiny, uniform region into something vastly larger, far larger than what we can now observe. The uniformity we see today reflects the uniformity that existed in that much smaller pre-inflation region. But inflation also preserved tiny quantum fluctuations that existed in that early universe. These microscopic irregularities in density, random variations that occurred at the quantum level, were stretched by inflation into cosmic scale variations. These became the seeds from which all large-scale structure eventually grew. Regions that were slightly denser than average had slightly stronger gravitational fields, which attracted additional matter, making them denser still. Over hundreds of millions of years, these enhanced regions pulled in enough matter to form the first stars, then the first galaxies, and eventually the vast cosmic web of galactic clusters and superclusters we observe today. The light from the Big Bang that we detect as the CMB wasn't actually emitted at the very beginning. For roughly the first 380,000 years after the initial expansion, the universe was opaque to light. It existed in a state called a plasma, where matter was so hot and dense that electrons couldn't remain bound to atomic nuclei. Photons, particles of light, couldn't travel freely through this plasma because they constantly collided with and were absorbed by free electrons. The universe was filled with light, but that light couldn't propagate freely. It was trapped, constantly being absorbed and re-emitted, unable to stream across space. As the universe expanded, it cooled. Eventually, it cooled enough that electrons could combine with atomic nuclei to form stable atoms, primarily hydrogen and helium. This transition, called recombination, fundamentally changed the universe's transparency. Once electrons were bound into atoms, photons could suddenly travel freely without constant interference. The universe became transparent, and light could stream across cosmic distances. The CMB represents the light that was released during this transition, the first light that could freely traverse the cosmos. When we detect the CMB, we're seeing the universe as it appeared 380,000 years after the initial expansion, the earliest moment at which electromagnetic radiation could propagate freely. Everything that occurred before recombination remains hidden from us, inaccessible through conventional astronomical observation. We can't see earlier than the CMB using light, because before recombination, light couldn't travel freely. The CMB forms an opaque barrier beyond which optical and radio astronomy cannot penetrate. However, this doesn't mean we're completely blind to earlier moments. Other forms of observation might someday allow us to probe deeper into cosmic history. Gravitational waves, for instance, can propagate freely through matter and plasma. If we could detect primordial gravitational waves from the very early universe, a monumental technical challenge but potentially achievable, we might glimpse conditions that existed before the universe became transparent to light. The discovery of cosmic expansion and the CMB established what's called the Standard Model of Cosmology, often referred to as the Lambda CDM model. Lambda represents the cosmological constant, Einstein's term for dark energy. CDM stands for cold dark matter, another crucial component of the universe that we'll need to understand. This model successfully explains an enormous range of observations: the expansion of space, the age of the universe, the relative abundances of different elements, the formation of large-scale structure, and the properties of the CMB. It's been tested against countless observations and has passed every test with remarkable accuracy. Yet despite its success, the Lambda CDM model reveals that we understand surprisingly little about the universe's actual contents. When cosmologists add up all the matter and energy in the universe and categorize it by type, they reach a startling conclusion. The ordinary matter that makes up everything we can see, stars, planets, gas clouds, you, me, everything composed of atoms accounts for less than 5% of the universe's total mass-energy content. Let that sink in for a moment. Everything we've ever observed directly, every star visible in every galaxy we photographed, all the gas and dust scattered through space, represents less than 1/20th of what's actually out there. So what constitutes the remaining 95%? Roughly 68% of the universe's mass energy exists as dark energy, the mysterious force driving cosmic acceleration. We can measure its effects through the expansion rate, but we don't understand its fundamental nature. We don't know why it exists, what it's made of in any meaningful physical sense, or why it has the particular density it does. The remaining 27% or so consists of dark matter, the cold component referenced in Lambda, CDM. Dark matter doesn't emit, absorb, or reflect light. It's invisible to all electromagnetic radiation. We know it exists only through its gravitational effects. The evidence for dark matter comes from multiple independent observations. When astronomers measure how fast stars orbit within galaxies, they find something unexpected. Stars far from a galaxy's center orbit, much faster than they should, if only the visible matter were providing gravitational attraction. The same problem appears when looking at how galaxies move within clusters. Individual galaxies orbit around their cluster's center, far too quickly to be held in place by the gravitational pull of all the visible stars and gas. Without some additional unseen mass providing extra gravity, these fast-moving stars and galaxies should have been flung out into intergalactic space long ago. Yet they remain bound to their galaxies and clusters, which means additional mass must be present, mass we cannot see. Another compelling line of evidence comes from gravitational lensing. Einstein's general relativity predicts that massive objects curve space-time, and this curvature bends the path of light passing nearby. When light from a distant galaxy passes close to a massive galaxy cluster between that source and Earth, the cluster's gravity bends the light, distorting and magnifying the distant galaxy's image. By measuring this distortion, astronomers can calculate the total mass of the intervening cluster. When they do this, they consistently find that the cluster contains far more mass than can be accounted for by all the visible stars and gas. The extra mass required to explain the lensing must be some form of invisible matter. Perhaps the most dramatic evidence comes from colliding galaxy clusters. When two clusters collide, the hot gas they contain interacts, creating friction that slows the gas down. But the stars and dark matter pass through relatively unimpeded, because the distances between individual objects are so vast that direct collisions are rare. In a system called the bullet cluster, astronomers observe the aftermath of such a collision. By mapping the visible light, they could see where the stars are. By observing X-rays emitted by hot gas, they could see where the normal matter concentrated. After the collision, it had been slowed by the interaction and lagged behind. But by measuring gravitational lensing, they could map where the total mass is located. The mass distribution showed two large concentrations that had passed through each other and continued beyond where the gas had stopped. This provides direct evidence that most of the cluster's mass exists in some invisible form that doesn't interact through electromagnetic forces, but does interact gravitationally. Despite overwhelming evidence for its existence, we still don't know what dark matter actually is. It's not simply normal matter that's too dark to see. It can't be clouds of gas or failed stars or black holes, because those would affect light passing through or near them in ways we detect. Dark matter must be something else entirely. Some type of particle that doesn't interact with electromagnetic radiation, but does have mass and therefore gravitational influence. Physicists have proposed numerous candidates. WIMPs, weakly interacting massive particles, are a popular theoretical possibility. Actions, extremely light hypothetical particles, are another candidate. Some theories suggest sterile neutrinos or other exotic particles. Despite decades of experimental searches, we haven't detected dark matter particles directly. Experiments deep underground shielded from cosmic rays and other interference. Search for rare interactions between dark matter particles and ordinary matter. So far, no definitive detection has been made. The nature of dark energy is even more mysterious than dark matter. At least with dark matter, we understand what role it plays. It provides extra gravitational attraction that holds galaxies and clusters together and shape the formation of cosmic structure. Dark energy's role is clear. It drives the accelerated expansion of space, but its fundamental nature is deeply puzzling. The simplest explanation is that dark energy represents the energy of empty space itself, a baseline energy density inherent in the vacuum. Quantum field theory predicts that even empty space should have some inherent energy due to quantum fluctuations, temporary particle-antiparticle pairs that constantly pop into and out of existence. When physicists calculate what this vacuum energy should be, they get an answer that's wrong by an almost incomprehensible factor about 10 to the power of 120. This is arguably the worst theoretical prediction in the history of physics. Clearly, either the calculation is wrong, or some unknown mechanism cancels out most of the vacuum energy, leaving only the tiny amount we observe as dark energy. We don't know which explanation is correct, or if the truth is something else entirely. Some physicists propose that dark energy isn't constant but changes over time, perhaps connected to some undiscovered field, similar to the field that drove cosmic inflation. Others suggest our observations might be explained without dark energy if general relativity breaks down at cosmic scales, requiring modification to Einstein's equations. But so far, all the evidence supports the simple lambda CDM model with a constant dark energy density, even though we can't explain why it has the value it does. The accelerating expansion driven by dark energy has profound implications for the universe's far future. In the early universe, when matter and radiation were more concentrated, gravity was the dominant force. Matter attracted other matter, pulling regions together into ever denser clumps that eventually formed galaxies. But as the universe expanded and matter became more dilute, the relative influence of dark energy grew stronger. Dark energy's density remains roughly constant per unit volume, even as space expands, while matter density decreases. Eventually, dark energy came to dominate, and the expansion rate began accelerating. As time goes on, this acceleration will continue to increase. Distant galaxies are already receding from us faster than light speed due to the expansion of intervening space. As expansion accelerates, more and more galaxies will cross the cosmic horizon, the boundary beyond which objects recede faster than light. Once a galaxy crosses this horizon, we can never receive any new light from it. The light it emits continues traveling toward us, but space between us expands faster than light approaches, so the light never actually gets any closer. These galaxies effectively disappear from our observable universe, not because they've been destroyed, but because the expansion of space has carried them beyond the reach of observation. In the extremely distant future, trillions upon trillions of years from now, the Milky Way and its immediate neighbors, gravitationally bound together in what's called the local group, will be the only galaxies we can observe. Everything else will have been carried beyond the cosmic horizon by accelerating expansion. An astronomer living in that era, looking out into space with even the most sophisticated instruments imaginable, would see only a handful of nearby galaxies surrounded by infinite darkness. They would have no evidence that billions of other galaxies exist, no way to know that the universe extends far beyond what they can see. They might reasonably conclude that their small cluster of galaxies represents the entire universe. This raises a profound and unsettling question. How much of the universe lies beyond our own cosmic horizon right now? What vast structures, what extraordinary phenomena exist in regions of space that are forever inaccessible to our observation? The light from these regions can never reach us, not because the light isn't traveling toward us, but because the space between us expands faster than light can cross it. These regions are not merely distant, they are fundamentally unreachable, causally disconnected from our portion of reality. We can never observe them, never send signals to them, never interact with them in any way. For all practical purposes, they exist in a separate universe, even though they're part of the same continuous space. This realization forces us to reconsider what we mean when we use the word universe. Traditionally, the term referred to everything that exists, the totality of space, time, matter, and energy. But our observations only give us access to a finite bubble, that sphere of space from which light has had time to reach us since the beginning. Beyond our observable universe lies the unobservable universe, regions of space that are just as real but forever beyond our detection. Some cosmologists prefer to use the term universe only for the observable portion and introduce the word cosmos or megaverse to describe the potentially infinite totality of existence. Others continue using universe for everything while distinguishing between observable and unobservable regions. Regardless of terminology, the question remains, how large is the universe beyond what we can see? Is it merely somewhat larger than our observable bubble, or vastly larger, or perhaps even infinite? The cosmic microwave background gives us crucial clues. If the universe were finite and small enough, we might expect to see patterns in the CMB that repeat, similar to how you might see your own reflection repeated multiple times if you stood in a room whose walls were perfect mirrors. Light could potentially travel all the way around a finite universe and return from the opposite direction, creating detectable repetition in the background radiation. Careful analysis of the CMB has searched for such patterns and found none, which suggests that if the universe is finite, it must be at least several times larger than our observable portion, possibly much larger. Many cosmologists believe the universe may actually be infinite, extending forever in all directions with no edge or boundary. This seems to follow naturally from the theory of cosmic inflation. If a tiny region of space underwent exponential expansion during the inflationary epoch, and if that expansion lasted even slightly longer than the minimum time required to explain our observations, the resulting universe would be incomprehensibly vast, effectively infinite from any practical standpoint, even if technically finite. Moreover, some versions of inflation theory suggest that inflation, once started, never completely stops. In certain regions, inflation ends and normal expansion takes over, creating bubble universes like our own observable region. But in other regions, inflation continues, spawning more bubble universes in an eternal process. This scenario, called eternal inflation, would produce an infinite megaverse containing infinitely many bubble universes, each potentially with different physical properties. The possibility of an infinite universe raises fascinating philosophical questions. In a truly infinite universe containing infinite matter, every possible configuration of particles would not only exist somewhere, but would exist infinitely many times. There would be infinite planets exactly like Earth, infinite versions of you reading these exact words, and infinite variations where events unfolded slightly differently. This seems absurd, yet it follows logically from infinity. If something has even the tiniest non-zero probability of occurring, and you have infinite opportunities for it to occur, it must happen infinitely often. Most physicists avoid dwelling on these implications, focusing instead on the observable universe where we can actually test predictions. The nature of cosmic expansion also affects our understanding of space itself. In everyday experience, we think of space as a fixed stage on which events occur. Objects move through space, but space itself seems static and unchanging. Cosmic expansion reveals this intuition to be wrong. Space is dynamic. It can stretch, potentially contract, and its properties can change over time. When we say space expands, we mean that the distance between any 2 points that aren't gravitationally bound together increases over time. Imagine marking 2 dots on a deflated balloon, then inflating the balloon. The dots move apart, but not because they're traveling across the balloon's surface. The surface itself is expanding, carrying the dots apart. Similarly, galaxies don't move through space away from each other. Space itself expands between them. This distinction becomes crucial when considering objects receding faster than light. If galaxies were moving through space, faster than light motion would violate relativity, but they're not moving through space that fast. Rather, the space between us and distant galaxies is expanding rapidly enough that the distance increases faster than light could cross it. There's no violation of relativity because the galaxies aren't actually moving faster than light relative to the space they occupy. The confusion arises from thinking of expansion as motion through space rather than the expansion of space itself. Understanding space-time as a dynamic entity rather than a fixed backdrop represents one of Einstein's greatest insights. General relativity describes gravity not as a force acting through space, but as the curvature of space-time itself. Massive objects create curves and warps in the fabric of space-time. and other objects follow the straightest possible paths through this curved geometry, what we perceive as gravitational attraction. This framework allows for phenomena that would be impossible if space were simply an unchanging container. Black holes, for instance, represent regions where space-time curvature becomes so extreme that not even light can escape. The event horizon of a black hole isn't a physical barrier, it's the boundary beyond which all paths through space-time lead inward, making escape impossible even at light speed. The relationship between matter, energy, and space-time curvature is described by Einstein's field equations, mathematical expressions that relate the distribution of mass and energy to the geometry of space-time. These equations are notoriously difficult to solve except in special cases with high symmetry. The expanding universe represents one such case. If we assume the universe is approximately uniform on large scales, the equations simplify considerably, leading to what are called the Friedmann equations. These describe how the expansion rate changes over time, depending on the universe's contents: matter, radiation, and dark energy. The Friedmann equations reveal three possible fates for the universe, depending on its density and the strength of dark energy. If the universe contained enough matter, gravity could eventually overcome the expansion, causing the universe to stop expanding and begin contracting in a big crunch, a time-reversed version of the Big Bang. If the universe contained less matter, expansion would continue forever but gradually decelerate, asymptotically approaching zero expansion rate. In a universe dominated by dark energy, as ours appears to be, expansion accelerates indefinitely, eventually tearing apart all structures that aren't tightly bound by gravity. Observations indicate we're in this third scenario. The universe will expand forever, and the expansion will accelerate. As mentioned earlier, distant galaxies will eventually recede beyond the cosmic horizon, but the effects of accelerating expansion extend beyond this. In the extremely far future, dark energy's influence will grow strong enough to overcome even relatively strong gravitational bindings. Clusters of galaxies will be torn apart as space expands faster than their mutual gravity can compensate for. Eventually, even individual galaxies might be disrupted, their stars scattered as expanding space overcomes galactic gravity. In the most extreme versions of this scenario, called the Big Rip, expansion eventually becomes so rapid that even atomic nuclei are torn apart. However, current observations suggest this extreme outcome is unlikely. Dark energy appears to have constant density rather than growing stronger over time, which would produce merely eternal expansion rather than a catastrophic rip. Long before any such dramatic ending, the universe will have undergone profound changes simply through the normal evolution of stars and galaxies. Stars form from collapsing clouds of gas, primarily hydrogen and helium left over from the Big Bang, along with heavier elements forged in earlier stellar generations. They burn through their nuclear fuel over millions to billions of years, depending on their mass, then die in various ways. Small stars fade to cold, dark cinders called black dwarfs. Larger stars explode as supernovae, scattering heavy elements into space and leaving behind neutron stars or black holes. The gas, ejected by dying stars, can participate in new star formation, recycling matter through successive generations of stars. But this process cannot continue forever. Each cycle converts some hydrogen and helium into heavier elements, and eventually, the supply of raw materials for new star formation will be exhausted. Within several trillion years, star formation will essentially cease. The universe will contain only long-lived red dwarf stars still burning their fuel, and the remnants of dead stars, white dwarfs, neutron stars, and black holes. Over time, even the red dwarfs will exhaust their fuel and fade to darkness. The universe will enter what's called the degenerate era, dominated by stellar remnants, gradually cooling toward absolute zero. But even this isn't the end. Over time frames that dwarf even these trillions of years, stellar remnants can potentially decay through exotic processes. Protons, long thought to be absolutely stable, might actually decay given enough time theories suggest timescales of 10 to the 35th years or longer. If proton decay occurs, even white dwarfs and neutron stars will eventually evaporate, leaving only black holes and individual particles scattered through an exponentially expanding void. The black holes themselves will ultimately evaporate through Hawking radiation, a quantum mechanical process by which black holes slowly lose mass. The largest black holes will take unimaginably long to evaporate completely, potentially 10 to the 100 years or more. After the last black hole evaporates, the universe will consist only of a dilute bath of radiation and elementary particles, spread across a volume that continues to expand exponentially. The temperature will approach absolute zero asymptotically, and the universe will reach a state of maximum entropy total disorder, with no available energy to perform work. This is the heat-death scenario, the ultimate fate of an eternally expanding universe. It's a state of absolute equilibrium, utterly cold, dark, and empty, with no possibility of structure, complexity, or anything we might recognize as interesting phenomena. These projections extend so far into the future that they seem almost meaningless. The timescales involved exceed our ordinary experience by factors so large they're essentially incomprehensible. Yet physics allows us to extrapolate current laws into the future and make predictions, however uncertain. These predictions assume that the fundamental laws of physics don't change, that dark energy remains constant, and that no unexpected phenomena alter the universe's evolution. All of these assumptions could be wrong. Our understanding of physics remains incomplete. We don't understand dark matter or dark energy. We haven't successfully unified quantum mechanics with general relativity, and we may be missing crucial pieces of the puzzle. Some physicists propose that the vacuum state of our universe might not be stable. The Higgs field, which gives particles their mass, currently sits at a particular value throughout space. But this might not be the true minimum energy state. There might exist a lower energy configuration. If so, quantum tunneling could eventually cause a bubble of this lower energy vacuum to form somewhere in the universe. This bubble would expand at light speed, converting the existing vacuum into the new lower energy state. Depending on the properties of this new vacuum, physical laws might be different inside the bubble. Particles might have different masses, forces might have different strengths, and the universe as we know it would cease to exist wherever the bubble passes. This is called vacuum decay, and if it occurs, it would represent a true ending, not a gradual fading into cold darkness, but a sudden transformation of physical law itself. The probability of vacuum decay depends on details of particle physics that we don't fully understand. Current measurements of the Higgs field's properties suggest we might be in a metastable state, not the absolute minimum energy, but a local minimum that's stable enough to last for an extremely long time, potentially much longer than the current age of the universe. But we can't rule out the possibility that vacuum decay could occur at any moment. If a bubble of new vacuum forms anywhere in the universe, there's no warning it expands at light speed, and we'd have no indication anything was wrong until the moment it arrived. This sounds alarming, but the probability appears to be extraordinarily low, and there's nothing we could do about it anyway. It's simply one of many ways the universe might fundamentally change in ways we can't predict. Returning to our present era, we find ourselves in what might be called the universe's golden age. Stars are forming, galaxies are evolving, and complexity is possible. The universe has cooled enough from its initial hot, dense state for atoms to exist, for chemistry to occur, for planets to form. Yet it hasn't expanded so much that galaxy formation has ceased, or that stars have exhausted their fuel. The current era represents a brief window, cosmically speaking, when interesting things can happen. Life, consciousness, and intelligence appear to require this kind of complex environment. Not too hot, not too cold, with sufficient time for evolution, but not so much time that all stars have died. The fact that we exist to observe the universe at all requires certain conditions to be met. The universe must be old enough for stars to have formed and created heavy elements, and for those elements to be incorporated into new stellar systems where planets can form. But it can't be so old that all suitable stars have died. The fundamental physical constants must have values within relatively narrow ranges to allow chemistry and stable structures. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were different, atoms might not form stable molecules. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to form. This observation that the universe appears finely tuned for our existence leads to much philosophical and scientific debate. Some see it as evidence for design, suggesting that the universe was intentionally configured to allow life. Others invoke the anthropic principle. We necessarily find ourselves in a universe capable of producing observers, because if the universe couldn't produce observers, we wouldn't be here to notice. In a megaverse containing infinite or near-infinite variations, some regions would inevitably have the right properties for complexity and life, and observers would necessarily find themselves in those regions. These questions touch on the deepest mysteries of existence. Why is there something rather than nothing? Why do the laws of physics have the particular form they do? Is our universe unique? Or does it represent one possibility among many? We have mathematical frameworks that describe how the universe behaves. But mathematics can only take us so far. It can't tell us why these particular equations govern reality rather than different equations, or why mathematics describes reality at all. Despite these deep uncertainties, the observable universe offers more than enough to occupy human curiosity. We've barely begun to catalog the phenomena occurring within our cosmic bubble. Every generation of telescopes reveals new surprises, objects, and events that challenge our understanding and require new theoretical frameworks to explain. The universe consistently proves to be stranger and more wonderful than our theories predict. From dark matter and dark energy to black holes and neutron stars, from the cosmic web of galactic filaments to the detailed structure of the CMB, observations continue to surprise us. Looking outward into space also means looking backward in time. Because light takes time to travel, distant objects appear as they existed when their light began its journey toward us. The most distant galaxies we observe appear as they were more than 13 billion years ago, when the universe was young and galaxies were just beginning to form. These ancient galaxies look different from nearby modern galaxies. They're smaller, more irregular, more actively forming stars. By observing galaxies at different distances, and therefore different ages, we can trace the evolution of galactic structure across cosmic time. Future telescopes will probe even deeper, potentially detecting the first stars that formed after the Big Bang, objects that existed when the universe was only a few 100 million years old. These first stars, called population 3 stars, would have contained only hydrogen and helium. No heavy elements yet existed. They were likely extremely massive and short-lived, exploding as supernovae after only a few million years and seeding the universe with its first heavy elements. No population 3 star has been definitively observed, but upcoming instruments might finally detect them, giving us a glimpse of the universe's first stellar generation. Each new observation refines our understanding, answering old questions while raising new ones. The discovery of the CMB confirmed the Big Bang model, but raised questions about the universe's uniformity that led to the inflation theory. The discovery of accelerating expansion answered questions about the universe's fate, but introduced the mystery of dark energy. The observation of galaxy rotation curves revealed dark matter, but left us uncertain about its particle nature. Science progresses, not by finding final answers, but by asking better questions, each answer leading to deeper inquiry. We are, in a very real sense, the universe becoming conscious of itself. The atoms in your body were forged in the cores of ancient stars, scattered into space when those stars died, and eventually incorporated into new stars, planets, and ultimately living beings. We are literally made of stardust, organized into structures complex enough to contemplate their own origins. Every thought you have, every observation you make, represents matter and energy arranged in a configuration that allows the universe to examine itself. Consciousness appears to be an emergent property of sufficient complexity, arising naturally when matter organizes itself in particular ways under the right conditions. The universe's edge, that boundary of observable space marked by the cosmic microwave background, represents a fundamental limit to our knowledge. We can never see beyond it using electromagnetic radiation. We can never know directly what lies in those forever unreachable regions. Yet we can extrapolate, using the laws of physics we've discovered through observation and experiment. We can make educated guesses about what the unobservable universe might contain, even while acknowledging that these guesses might be wrong. What we've learned about the observable universe suggests that the cosmos beyond our horizon is probably similar to what we see within it. More galaxies, more stars, more planets, perhaps more life. Or perhaps not. Perhaps conditions vary across the cosmos, with some regions dense and rich in structure, others sparse and empty. In an infinite universe, every possible configuration would exist somewhere, but we can only study the one region accessible to us. This cosmic bubble centered on our location in space and time. The edge of the universe, then, is not a wall or barrier, but a horizon. A boundary beyond which observation becomes impossible not because of technological limitations, but because of fundamental physics. Light from beyond this horizon will never reach us. As the universe ages and expansion continues, this horizon will actually shrink in a certain sense. Galaxies we can see today will eventually cross the boundary and disappear from view. The observable universe will contain less and less, even as the universe as a whole grows larger and larger. Yet for now, for this moment in cosmic history, we have access to a vast expanse of observable space containing hundreds of billions of galaxies, each containing billions or trillions of stars. We live in an era when observation and understanding are possible, when the universe reveals its nature to those who look carefully enough. We stand at a unique vantage point in time and space, able to observe the cosmos and decode its history, to trace events from the earliest moments after the Big Bang to the present day, and to project forward into the unimaginably distant future. The universe is both more vast and more comprehensible than previous generations could have imagined. We've measured distances that exceed human intuition, timescales that dwarf historical experience, and energies that boggle the mind. Yet, through careful observation, mathematical reasoning, and physical theory, we've constructed a coherent picture of cosmic evolution, from the earliest fractions of a second to trillions of years hence. We've identified the major components of the universe and traced how they interact and evolve. We've discovered that the universe had a beginning, that it's expanding, and that this expansion is accelerating toward an ultimate ending in cold, dark emptiness. And we've learned that our position in the cosmos is utterly ordinary. We're not at the center of anything. Every observer is at the center of their own observable bubble. Our galaxy is unremarkable, one among hundreds of billions. Our star is average, one of countless similar stars. Our planet, while precious to us, is simply another world among the countless trillions that must exist throughout the universe. Yet, despite this cosmic insignificance, we remain significant in our own sphere. We are the observers who can comprehend these vast scales, who can trace cosmic history, who can ask questions about existence and meaning. The edge of our observable universe marks the limit of what we can see, but not the limit of what we can know or imagine or wonder about. Beyond that edge lies more universe, more space, more possibilities, forever beyond our reach, yet connected to us through the continuous fabric of space and time. We exist within a bubble of light surrounded by an ocean of darkness, and that darkness represents not emptiness, but simply the unknowable vastness of a cosmos too large for any finite being to fully comprehend. And perhaps that's exactly as it should be, a universe grand enough to humble us, yet comprehensible enough to reward our curiosity.